In this section, we'll talk about validating machine learning-based systems. When considering how to make sure that an automated vehicle can drive as well or better than a human, it's common to propose the idea of passing a driver test. After all, if you want an automated driving system to drive as well or better than a human, then if it can pass the human driver test, then why wouldn't it be okay to go on the road? Well, it turns out there's a problem, but let's get there by steps. Ask yourself, what are the pieces to a driver test? Well, there's the written test, such as does the ADS know traffic laws and does it know the proper behavior in various situations? Exactly the kind of things that computers should be good at knowing. For example, if two cars stop at stop signs, which one goes first? Those rules are all in the driver's manual, so that ought to be the easy part. Well, what's another part of passing a human driver test? That's the road test. So you take the vehicle that has the automated driving system out on the road and you see if it can execute the traffic laws properly. Can it negotiate effectively with human drivers to determine right-of-way? Can it exhibit good driver hygiene? And can it resolve potentially ambiguous driver situations? For example, if cars get to an intersection with four-way stop signs at exactly the same time, can it figure out who's going to go first? While the road test is a lot more challenging than a written test equivalent, that's pretty much the target of billions of dollars of spending. And so one can believe that in order to be able to drive on the road, it should be able to pass more or less the equivalent of a human road test. But those two things, the written test and the road test, are not the only pieces of a driver test. There are, to be sure, some other things such as perhaps a vision test and so on. But the biggest remaining thing we haven't talked about is the part where, in order to get a driver's license, you have to be a 16-year-old human being, with that age varying depending on the local regulations. Well, what's the relevance of a 16-year-old human being? The thing is that 16-year-olds have a certain level of maturity that as a society we've decided is sufficient to go on the road, perhaps with a junior permit or a learner's permit, but nonetheless, at 16, we've decided the 16-year-old human has enough experience and enough judgment maturity to be allowed out on the road to begin the process of maturing into a fully capable driver. How do you decide that an automated driving system on a computer has enough judgment maturity? Waiting until the code's 16 years old is certainly not going to do it. And a lot of this boils down to, does the ADS know when it doesn't know what to do? Humans have their issues with being able to follow directions consistently and pay attention all the time. But a computer-based system, especially one based on machine learning, has a huge blind spot in that they're much worse than humans at knowing when something weird is going on that they've never seen before. Humans are pretty good at saying, something weird is going on, I think I'm going to take it easy until I figure it out, whereas an ADS-based system is much more likely to blindly go ahead, supremely confident in its abilities in a situation that it's actually never been trained for. So the issue with the driver's test is, how do you know that the ADS is sufficiently mature to be allowed to drive, even if it's mastered the basic skills and knowledge? A significant challenge to validating autonomous vehicles is the fact that they tend to use machine learning-based approaches to perception and other tasks. In a nutshell, machine learning involves an inductive learning approach in which you collect lots of training data, use that training data to learn a model, then you adjust the learned model and iterate until you pass all the tests. In other words, you show the system a lot of examples. This is a person, this is a person, this is not a person, that's a tree, that's a car, and so on. And over many iterations across lots of data, the model is adjusted until it gives statistically very good answers. When you show it a person, almost all the time it'll say, yes, that's a person. When you show it a car, it'll say, yes, that's a car, and so on. There are some fundamental challenges to this approach, though. You're not actually teaching it what a person looks like by describing a person. It's learning by example. Challenges that result from that approach include asking what happens if it sees a novel input. If you've shown it a bunch of people and it sees a person that doesn't quite look like the people it's seen, will it get it right or will it get it wrong? One problem comes with so-called overfitting. If you think about showing machine learning-based system 1,000 pictures of people, If it overfits, it will recognize those exact 1,000 photos and nothing else. So the idea is you want to train it so that it not only recognizes the pictures it's seen, but pictures that are close to the pictures it's seen in some statistical sense. A model that is overfitted is too brittle to small changes in input data and can perform poorly on novel inputs. There's also the possibility of gaps in training data. If there are categories of things that exist in the real world that it's simply never seen, it can't learn them. Those gaps could include skin color, clothing color, unique postures, and so on. Another fundamental challenge is deciding whether it learned what you hoped it learned. Machine learning-based systems are notorious for gaming things. As a purely hypothetical example, if all your training data had people in hats because it was done in a cold winter, then it might struggle with people who don't have hats on because it may not have learned what a person looks like at all. It might simply have learned to recognize hats. While that idea might seem a little far-fetched, in fact, these systems are notorious for gaming easy statistical patterns in data that the people designing the system didn't really realize were there until after they saw the system's behavior. In the end, the fundamental issue for validation is you know the system learned something, and you know that statistically it works pretty well on the inputs you give it for both training and testing. But you don't actually know what it learned. And many times it learns what you hoped it learned, but sometimes it doesn't, and it's very difficult to tell what it may accidentally have learned through accidental patterns in the data that you didn't really even realize were there. There's a famous cartoon that summarizes the quandary of using machine learning-based systems. This cartoon is not entirely fair to the current state of the art, but it illustrates the main issue. You pour the data into this big pile of linear algebra and get an answer out the other side. Well, what if the answers are wrong? Well, stir the pile around until they start looking right. While that may be a bit unfair, it's not a bad explanation of how machine learning-based system training works. And the issue is, you know that the answers to the questions you thought to ask it during testing come out pretty well, but it's difficult to explain why the answers are right and whether or not that's because the system has learned the fundamental concepts you want to teach it, or whether it's just getting lucky. The issue with machine learning-based systems being designed by training versus intentional design raises a significant issue when you attempt to introduce that technology into a traditional software safety V cycle. In a traditional V, there's requirements and design on the left of the V and verification validation on the right side of the V. If you use a machine learning-based system with inductive training, there are no requirements, and there is no traditional design. For example, if you're building a machine learning-based system to detect people, there's no place where the designer says, here's what a person looks like. There's a head, and there's a torso, and so on. That never happens. You just show the system a bunch of pictures of people and say, these are all people, figure out what it means to be a person. So there's no intentional design, and more importantly, there's no insight into what the machine learning system is really learning. It just learns how to come up with answers that have a good statistical correlation to the training set. Well, that's all well and good if it seems to work, but how do you validate it? The point of the V is not simply to randomly test. The point of the V is that the tests on the right side correspond back to the left side and say, you meant to do a certain thing, and sure enough, you did it. Well, sure, there's some element of this in that you have a testing data set and you say, well, the machine learning system seemed to learn what we wanted it to learn because it did well on test inputs. But that's not quite the same as the V, largely because you cannot explain why it works. And so you have no confidence that it's working for the right reason, as opposed to random statistical chance just happens to get lucky on the particular training data and the particular testing data. The result is you have a system that's inscrutable and in practice can be quite brittle. Dealing with this brittleness in validation is a significant issue in ensuring the safety of autonomous vehicles. When you have machine learning-based systems, it's difficult to apply traditional safety engineering processes such as the V model. Nonetheless, life-critical systems require extreme levels of reliability and safety. So what do companies do? Well, at first, the companies took to public road testing. And the idea was quite simply drive around a lot and get to the point where you build confidence in the safety of the technology through sheer brute force public road testing. This public road testing is good for identifying the easy cases. If your car struggles to get down a single block, public road testing will reveal that pretty quickly and give you some indication of how you're doing. After initial bouts of public road testing, two issues became obvious. The first is that it's expensive. Getting the vehicle to go a short distance or even a few miles between issues can be done pretty readily on public road testing. But when you want to graduate from tens or hundreds of miles to tens or hundreds of millions of miles between events, public road testing for millions of miles gets extremely expensive. Another issue is that public road testing is potentially dangerous. Running a closed-loop system in which the sensors on the car are fed into an automated vehicle control system and actually controlling that vehicle exposes the test platform to the potential for injuring or even killing other road users. And unfortunately, this happened in Tempe, Arizona in 2018, resulting in a fatality. Until that time, many of the companies were simply doing brute force road testing, but that event caused many of the companies to take a step back and say, maybe we should be doing less public road testing and think of other ways to validate the system. In reality, brute force public road testing was never going to produce enough miles to ensure that a system was suitable for life-critical application. To understand that, we have to think a bit about the number of miles that would take to prove that something is safe enough. Let's say that you have 200 million miles between fatal mishaps. That's about twice as far as the number of miles between fatalities in the US, but those fatalities include impaired drivers and other issues. So if we want to be as good or slightly better than a capable, unimpaired, well-behaved driver, we might say we want 200 million miles between fatalities to claim that we're good enough that we're not making things worse by deploying. Well, how long do you have to test to know that your vehicles are 200 million miles between critical mishaps? A little bit of statistical theory says that you need to test 3 to 10 times longer than the inter-arrival time between the mishaps. If you suffer no mishaps at all, it's about 3 times longer, but if you do get unlucky and get in a crash, you may need to go to 10 times longer to get statistical significance to show that you're crashing less often than a capable human driver. At 10 times longer, that's 2 billion miles of testing. 2 billion is the kind of number that has enough zeros it's hard to wrap your mind around. But if you look at Wolfram Alpha and ask how many miles of public road in the world, what this works out to be is about 50 round trips on every road in the world. And during that entire time, you need fewer than about 10 fatalities. That's a lot of driving. And even for the resource-rich companies that have embarked on this project, that's still an unaffordable cost. And don't forget, the answer might be you're not safe enough. What if it turns out your vehicle is not as safe as a human driver? You get to fix the problems, reset the testing odometer to 0, and do another couple billion miles. This illustrates that while public road testing might be a good way to get a little bit of experience if you can ensure it's done safely, and is certainly an important piece of a validation program, pure brute force road testing and nothing else will not get you to the point that you can declare you are as good as a human driver. It's simply too many miles, too expensive, and it takes too many vehicles spending too many years driving around roads. Compared to public road testing, you can do safer testing by using closed-course testing approaches. In this approach, a dedicated facility with controlled access is used to run tests on vehicles. This approach is expensive because a dedicated facility must be leased and maintained. It's poorly scalable because there are only a very few such facilities and they can only hold so many vehicles at a time. Closed-course testing can be very good for running high-risk scenarios that should not be attempted on public roads with controlled conditions, but they are limited to only test things you have thought of. As an example, you can see Volvo running a moose avoidance test using a dummy moose. But they famously had a problem the first time they encountered kangaroos when testing in Australia, because they had not designed the distance estimation software in their vehicle to be able to deal with a large animal that has all its feet in the air at the same time. While safety validation will always require some level of road testing and closed course testing, achieving high scalability will, as a practical matter, require simulation. Simulation involves a fidelity versus cost trade-off, but at some point, even a very high fidelity simulation is less expensive than putting a physical car on public road with safety drivers and so on. Good simulation requires more than a capable simulation engine. It also requires highly detailed models to run through the simulator. To validate the simulation, there's a challenge of matching real-world data to corresponding simulation models. But the biggest issue with simulation is that it only tests the things you have thought of. The most accurate, highest fidelity simulator in the world cannot create something like a kangaroo out of thin air if no model of a kangaroo has been put into the simulation. While simulations are expected to be cheaper at scale than public road testing, there is a considerable amount of design effort that needs to go into creating the simulation models as well as the experimental design. A common approach to simulations is to manage the simulation campaign by covering scenarios, where a scenario is a short sequence of positions and activities involving a number of objects. A very simplistic way to start building a scenario catalog is to look at pre-crash scenarios to make sure you're simulating the kinds of driving situations that tend to lead to crashes so you can avoid them. But after that starting point, you need to cover all the possible situations your vehicle can get into to make sure that it can not only avoid crashes, but also drive and not cause crashes and not suffer from crashes caused by situations that a human driver would find easy, but that the ADS would for some reason struggle with. The Pegasus project is a multi-year effort to create a methodical approach to identifying and assembling the scenarios required for an automated vehicle, as well as define a simulation execution platform to run simulation campaigns for validation. The thing to get out of this picture is that creating a simulation for automated vehicles, as well as being able to run across all the scenarios that matter, is a complicated proposition and takes significant engineering effort to set up and execute. When setting out to run a simulation campaign, it's important to realize that running simulators requires more than just a simulation engine. You need the autonomy functions that you intend to put in your vehicle, and you do need a simulation engine that has a physics engine and a rendering engine and so on. But for that simulator to do anything useful, you'll need a number of additional inputs. You'll need some workloads, such as a library of scenarios that you want to test, which will include some amount of synthesized information as well as recorded information to reproduce real-world scenarios you've driven in a real car for comparison, but also to create other scenarios that never happen in the real world, but you need to make sure are covered for your validation effort. You'll also need to design pass-fail metrics. While some metrics might seem trivial, such as you should not hit other cars, the nuances quickly escalate as you realize there might be some cases in which there's a no-win situation where you're trying to minimize collision speed rather than totally avoiding a hit. And there are likely to be near-miss criteria that you want to make sure you're a certain distance away from objects rather than barely avoiding impact when there was no need to be that close. Additional inputs needed for a simulation campaign include a bunch of models. You'll need models of the roads, of the weather, of the sensors, of the vehicle dynamics, of other road user behavior, of faults and failures that could occur that you need to be able to deal with, and a definition of what safe behavior actually means. You'll also need a rigorous design of experiments. There will be way too many combinations of all the conditions across all these models to run every possible simulation. So you'll need a structured approach to make sure that you squeeze the most information out of the simulations you can afford to run, and that you run enough simulations to provide sufficient confidence of safety at the end of the simulation campaign. When doing all those things, it's important to ask, what if there are simulation or software model defects? What if the simulation gives the wrong answer? What if the model in the simulation is too different from the real world and it gives misleading results? Ask yourself, is it possible that someone will die in a real vehicle because there was a simulation defect that missed a critical thing that will later on cause a fatality in the real world? And beyond all this, it is very common for simulation campaigns to assume perfect perception and just run the physics of all the different vehicle motions. But in fact, perception may be the hardest part of this entire system. So if your simulation approach includes perception, that's great. There's a whole bunch more detail there. But if it does not include perception, ask yourself how you plan to make sure that your perception system is good enough. A simulator and all the models and all the design of experiment work that go with it end up being a very substantial, complex software system. We all know that software can have defects. So this raises the question, how do you know that your simulation results are actually correct? How do you know that the simulation really predicts the behavior you will experience with a real vehicle on a real road, especially for scenarios that were only covered in simulation and that were not covered on a real road? There are two high-level issues to consider. The first is model accuracy and tool qualification. How do you know that your model of your environment is correct? That your own vehicle and other road users behave in the simulation the way they would in the real world? How do you know that perception as well as vehicle motion is covered? And how do you know that you've considered the right safety metrics to be monitoring during the simulation? Ultimately, this comes down to comparing the behavior of the real world with the behavior of the simulation and making sure that they're close enough that the expected safety prediction of the simulation campaign is predictive of the expected safety performance in the real world. In addition to purely experimental results, there will be a need for some level of tool qualification. Consider, if your simulation has really poor quality software that's full of bugs, it's unreasonable to expect it to produce high quality results simply by running a bunch of tests and comparing against the real world. There will be some instances of incorrect behavior due to those bugs that you might not catch during those comparisons. So there's some minimum level of tool qualification that needs to be performed to make sure your software is of high enough quality beyond just running some tests and compares. The second high-level issue for simulation validation is experimental design. You can have the world's best simulators and the world's best models, but if you don't cover the entire operational design domain of your vehicle in the simulator, then there will be pieces of the ODD that you did not stress during simulation, and who knows what will happen when the car experiences them in real life. Special emphasis should be placed on high-risk edge cases that may appear very infrequently but have high consequence. There may well be situations that only occur once every million miles in the real world, but if they have a high probability of leading to a crash, you need to be sure that they're appropriately handled by the vehicle, or you will not achieve your safety budget. Beyond making sure that your simulation campaign covers the whole ODD and edge cases, you have to make sure that validating the simulation also covers all the capabilities of the simulation. In general, this is going to require taking some real-world data and matching it to a corresponding simulation scenario. This turns out to require a significant amount of effort and is a big piece of the simulation validation engineering work. Finally, you have to make sure that the set of real-world driving you use to validate the simulation covers all of the ODD for the vehicle, as well as providing a high degree coverage of potential bugs inside the simulation. There's a famous saying that goes with this, which is, all models are wrong, but some are useful. You will never get a simulation that is perfect in every respect, and in particular, you will never get a simulation of infinite fidelity. But the approach to addressing that is not to try and get perfect fidelity, because you will never get there and it will cost too much to even try. Rather, the important part is to ask, what question is the simulation trying to answer, and make sure you have the right types of fidelity in the right degree to give an accurate enough answer to the questions you're asking of your simulator to make sure that the simulation results are predictive of safety in the real world. A complication of simulation campaigns for machine learning-based systems is that it can be not so clear what it means for a test to actually pass. With a traditional V model, the test paradigm is typically you think your design is right. You use your understanding of the design to create tests that validate that the design does what you think it's supposed to do. In other words, the test validates that the engineering was done properly, knowing that it probably was, and you're just looking for mismatches in the implementation. You tend to trace the tests to the requirements or the design. As a simple example, if you have 100 requirements, you might have 100 tests, and each one of the tests or test sets is designed specifically to look at a particular requirement to make sure the requirement made its way into the implementation. As a practical example, if you have a system that is supposed to detect a child in front of the vehicle and apply emergency brakes, putting a vehicle on a particular path and having a child-sized dummy cross in front of the vehicle and running that experiment a few times is likely sufficient to give you pretty good confidence that it works, because you have confidence that all the individual pieces work due to unit test and hardware-in-the-loop testing, and the only thing this particular closed course testing is doing is a graduation exercise to make sure you didn't miss anything during all the rigorous engineering and testing that went on before this. On the other hand, if you have an inductively trained system, such as based on machine learning, you don't actually know what all the detailed design is. What you know is that the system trained on some data and seems to look okay on tests, but you don't have a lot of confidence as to why it works. And this means in testing, there are a lot more unknowns you have to decide when interpreting test results. You think the system was trained properly, and the test is to determine whether the training worked to implement the real requirements rather than just being able to get through whatever test sets were applied to it. You have weak traceability between the real-world tests and the design because there is no design. So when you're doing testing, you're not only hoping to detect whether all the pieces work together in general, but also you're looking to detect training gaps, overfitting, and other potential failure modes of the machine learning system. But on top of that, you have a potentially non-deterministic, opaque design. What this means is just because something works once or twice or 3 times does not mean it will always work in situations that are even a little bit different. So you have to run many different tests with many different variations to make sure that you're not just happening to hit the sweet spots where the design works without falling into big gaps between training data points. Consider this situation in which a car is signaling via a smile on the front bumper that it sees pedestrians in the crosswalk. While you might run this test several times and the car always stops, what you don't know is why it's stopping. For example, maybe this vehicle only stops for baby carriages. Maybe it only stops for groups of people. Maybe it only stops for people wearing certain colors of clothing. Maybe it only sees one person and the smile's for that person, whereas the people off to the side will see the smile and think it sees them, but it doesn't. All these concerns can be addressed with a robust testing plan. But the point here is that 1 or 2 tests may not do it. You may need large number of tests and large numbers of combinations to really understand whether the system is behaving the way it is because it's properly interpreting the situation and doing the right thing, rather than getting lucky on a couple tests that happen to be the ones that you were running. A robust test plan that considers all the possible ways in which a system could be defective but still manage to pass tests is essential to make sure there are no gaps in the capabilities of the deployed system. The novel technology and complexity of autonomous vehicles requires significantly different approaches to validation than for traditional conventional vehicles. In particular, the use of machine learning and inductive-based learning techniques breaks the V design cycle because there's no requirement and design set to trace tests to. This leads to the need for a significantly more complicated and more rigorous testing approach. The cost of doing road testing means that simulation is going to be an essential technology for doing validation. But the simulation itself comes with significant complexity, including not only creating a good simulation engine, but also accurate models and a thorough test plan that provides appropriate coverage. The last piece is to remember that perception is arguably the hardest part of these systems, and many simulation approaches assume the perception is perfect and take it from there. Validating the perception part of these systems will be essential to ensure acceptable safety.